Hello, everyone. Thank you for attending. So it's a great pleasure to give this talk together with my great collaborator, Yunoki-san from RIKEN. And we'll be talking about how to enhance HPC simulations using error-mitigated quantum computers. So let me first begin by introducing the problem. The main problem with quantum computing at this time is the issue of errors and noise in quantum computers. We all know that noise severely limits the size of quantum computations that we can do with quantum computers. This problem can be remedied in two different ways. One of them is to use a large number of extra qubits in order to use error correction. These qubits also have to be of very high fidelity in order for this to be useful. The current devices don't have the numbers for making error correction still kind of useful in a practical sense. And the other way, other resources you could use is to use extra QPU time and use methods undergoing the name of error mitigation. And here the QPU time could be large. It's important to use a method that is very efficient. This is what we're focusing at Qedma. We've developed a software called KESM, which I'll introduce, which does this very efficiently. And this type of methods do not need any extra number qubit overhead. Furthermore, error mitigation could be combined together with error correction in order to give a significant extra boost over error correction, and can also be combined together with HPCs in order to boost performance, and this is going to be the focus on this talk. So let me discuss the possibility of obtaining a quantum advantage with error mitigation. So the time for performing error mitigation scales mildly exponentially with the circuit volume times the error rate. Now, this exponential scaling means that there cannot be an exponential quantum advantage, but there could be a polynomial advantage of a very high degree for quantum computing versus classical computing. And this polynomial could be of a degree of 1 over the error rate, which is very large. It could be in the order of 1,000. So this very large polynomial advantage can lead to dramatic finite quantum advantages. These are the practical quantum advantages we are interested in. In order to enjoy quantum advantage using error mitigation, it's of course important to use a method which is efficient in order to reach the largest circuit volumes possible, but it's also important to use a method which is unbiased, since in the regime of quantum advantage, you cannot verify your results anymore against classical simulations. In fact, using the devices that are available today, I'll show you that we're very close to achieving quantum advantage for executing circuits. And with next generation of devices, we're going to be in the quantum advantage regime. And furthermore, using the combination with HPCs, our work with RIKEN show we can really accelerate the timeline for achieving quantum advantage already today. So let me introduce KESM. KESM stands for Quantum Error Suppression and Error Mitigation. In Hebrew, KESM means magic. It is a few things I want you to keep in mind about KESM. One of them is that it's based on an unbiased method, meaning that when you execute the algorithm, you're getting results from a noise-free quantum computer. The only remaining sources of noise are statistical. This is an inherent part of quantum mechanics and can be reduced just by running for a longer time. The method works for any quantum algorithm. We refer to it as being algorithm agnostic. It also works for a variety of different quantum hardwares, and we've tested it also extensively. It also has a very flexible deployment that could be used either through our cloud, it could be installed on premises, or it could be used through a Qiskit function that we deploy. So let me give you a bird's eye view of how the software works. The end user sends our system the circuit he wants to run, the level of accuracy you want to get, and the specific device he wants to run on. Then based on this information, at the time of execution, we run a job for characterizing in a very precise way the noise sources in the device. Based on this, we optimize gates, we transpile the circuit, and we compile the circuit to an ensemble of quantum circuits, which we then execute on the device, and by classical post-processing, we return noise-free results to the user. To quantify the benefits of KESM, it's important to look at a quantity we call the circuit volume boost. This is the ratio between the largest volume you can reach with KESM over the largest volume you can reach just by running on the device with no error mitigation for a given accuracy. And this boost for high accuracy could become very, very large, on the order of 1,000. Again, this means that you can run a circuit that is 1,000 times larger than what you could do otherwise. You can also compare KESM to other competing methods that are unbiased, like probabilistic error cancellation, and you can see that KESM runs exponentially faster, giving you access to circuit volumes which are significantly larger. Before I show you some results, I want to introduce a quantity which is important in order to quantify performance, and this quantity is called the active volume. The active volume for a given circuit and observable you want to compute counts the number of 2-qubit gates that are affecting that observable. And this quantity quantifies all the complexity for performing error mitigation, since you only need to error mitigate gates within the active volume. It also quantifies how hard it is to do a classical simulation, since you only need to simulate the gates within this active volume. And the shape and the size of this active volume strongly depends on the parameters of the circuit. Here we are plotting it for a family of circuits called the Trotter-Kicht-Ising model, which we'll be using in the next slides. So here's a recent result from a Herm device. Here we used 130 qubits on IBM Marrakesh. We ran this Trotter-Ising circuits for 13 Trotter time steps. This is a large circuit. It's over 3,000 CZ gates. It is of depth 78. And we computed different observables here from single-point correlations to 4-point correlations. We compared them here to the ideal results, plotted in gray. The red points are the results you get by running on the device with no error mitigation. You can see that there's very big systematic errors. And the blue markers are the results we get with KESM, which agree very well with the correct results. On the right, you can also see how the active volume or the light cone evolves with the number of time steps, and you see that eventually at 13 time steps, it covers almost the full device. Here are some problems we worked on with our collaborators and partners. DESI is a group focusing on high energy, and they used KESM to study couplings in a U1 lattice gauge theory in 2+1 dimensions. They used the VQE approach and used KESM for executing the circuits. They also used KESM for a fluid dynamics problem in which they measured the moments of the velocity field. The quantum chemistry group at the University of Southern Denmark used KESM for performing VQE for the ground state of the H2O molecule. And the group of SoftBank used KESM in the QML algorithm in which they computed a kernel matrix using KESM. And you can see here the results. You can see the comparison between the ideal kernel matrix, the kernel matrix you could get when you run on the device with no error mitigation on the left. And you can see that there are very big systematic errors. And you can see on the right the results for the kernel matrix you get with KESM, which agree very well with the ideal result. So let me discuss the roadmap for achieving quantum advantage with KESM. In this plot, you can see the runtime of KESM as a function of the active volume for different values of the fidelity. You can also see how HPC state vector simulations scale as a function of this active volume. And you can see that with fidelities of 99.8%, you can already be in the quantum advantage regime for kind of generic circuits. And you can also see that the issue of the question of when do you cross in the quantum advantage regime also depends on the geometry of the specific active volume that you're looking at. So I want now to turn over the stage to Yunoki-san, who will tell us about really great collaboration in which we showed that the combination of KESM together with HPCs can enhance classical simulations already today. Okay, Yunoki-san.
Okay, thank you, Netanel. So let's wait. Oh, maybe I have to. Okay, at RIKEN, our team is mainly focusing on classical computations, particularly tensor network-based method. As a quick reminder, MPO and MPO-related approaches are very powerful classical approach to compress classical data. classical informations. And let's just assume that we have an operator O acting on n qubits. And in order to represent this operator, we generally need 4 to n parameters, and therefore it usually costs you like an exponentially large amount of computational time with increasing the number of qubits n if you want to treat this operator numerically exactly. However, the MPO and MPO-related approach provide you compressed representation of operator O as a product of matrices with bond dimension chi. And the computational cost for this approach scales as a chi cube, and therefore this is more convenient than the numerically exact approach. And this method is widely used in various research fields, including physics, quantum chemistry, and machine learning. And in this talk, we'd like to propose our new approach, which we would like to call quantum-enhanced MPO computations. And the key idea here is to apply simply a quantum circuit C onto a MPO and measure the expectation value of the resulting the operator using quantum computer with error mitigation. So as a use case example, we consider quantum dynamics that is split between quantum and classical computations. More precisely, we divide the total evolution steps, large T, into two segments. The first segment is performed on a quantum computer, while the second segment is handled using classical computers by back-propagating the operator or for time steps tau using MPO. And this approach allows you to evaluate the expectation value of the operator or of tau over a time-evolved state psi of small t by running the first part of the time steps using quantum computer. So to demonstrate our approach, here we consider a one-dimensional quantizing model on 75 qubits with these particular parameters where you can find discrete time crystal. And we measure a magnetization M over the entire qubits. And for all the experiments, we used IBM Heron 2 systems. And we set the classical evolution time tau, tau equal 10 steps. And without error mitigations, the estimated magnetization here represented by red circle here, deviates significantly from the ideal values shown in the gray. However, after applying the KESM for the error mitigation, the results shown in blue agrees quantitatively with the ideal value, or within the statistical error bars. More importantly, the time required to obtain this error mitigated magnetization is only 8 minutes here. For the total time steps 15 with classical time step 10 time steps. In contrast, if you use quantum computers alone to achieve the same statistical accuracy, the estimated the required QPU time would be increased up to like 240 minutes. And the benefit of our approach becomes more pronounced for a longer time steps, such as 25 time steps, where the required QPU time reduces from 17,000 minutes to 120 minutes if we use our approach. So using a very simple math with some reasonable assumption, one can estimate QPU time required scales according to the expression shown up there. There, chi-in is the bond dimension of the MPO that is calculated using classical computers. And IF is the infidelity of the quantum computers employed in your experiments. And the small t is the portion of the quantum portion of the time steps that you do in a quantum computer. Indeed, our experiments shown in the previous view graph scales very nicely according to this scaling form indicated by the straight lines here. Since the classical runtime required to extend the evolution by another time step small t scales exponentially, there is a very strong potential to realize quantum advantage provided that the infidelity of the quantum computers is sufficiently small. So finally, let me give you a concrete example by estimating the actual runtime. Let's just assume that we have an MPO with bond dimension 10,000, which is given in this estimate. So extending the evolution for another 5 time steps would require approximately 276 hours if you use one of the NVIDIA system. In contrast, the required time, the QPU time in our approach is just 30 minutes. Note that here also we have additional classical time, 17 hours, to decompose the MPO with bond dimension 1000. And the advantage of our approach becomes more clear for when the time step is extended to like 10 steps over there, here. The required, if you use classical alone approach, it requires like more than 3,000 hours, whereas our approach can still complete in just 3 hours. And then even more interesting, if the quantum computer reaches like a fidelity of 99.9%, the required QPU time to simulate up to like a 50 time step is only 3 hours. So these estimates strongly suggest that the quantum advantage may be achievable much sooner than previously expected, well before the full FTQC era. So please stay tuned because more interesting results are coming soon. Thank you.
Thank you very much. I think we have a question for Netanel, I believe. It's in Japanese, but I'll translate it. It's a two-part question. Is KESM a solution that is deployed on software? And second part is it reliant or upon IBM hardware?
Thank you. Yeah, so KESM is a software solution. It could be accessed through our own cloud. It's also integrated in a Qiskit function in IBM, but it is not specific for IBM hardware. We've tested it on a variety of different hardwares, including IonQ and IQM and other hardwares. So, it could be used on any hardware, and it needs just some adaptation in terms of the characterization part of the software.
Okay, thank you very much. Thank you again both to Yunoki-san and Netanel.